Okay, I think we should get started. You're all set in the back? Very good. All right. I'm Alan Downey. This is Bayesian Statistics Made Simple. So if that's not what you're here for, this would be a good time to leave. Just a little bit of background. I teach at Olin College, which is outside of Boston. It's in Needham, Massachusetts. Our mission is to fix engineering education. It's a new college, just started up about 15 years ago. And there's some of the projects that the students are working on. If you're interested, I can tell you more about that. But that's not what we're talking about today. I mentioned the web page here. Hopefully, you've all seen this. There are instructions there for getting set up. We'll talk a little bit more about that later on. Plan for the day, I'm going to start from pretty much nothing. I'm actually going to derive Bayes' theorem for you just to show that it's not magic. And from Bayes' theorem, we're going to get to doing Bayesian statistics and solving some examples that are real-world problems, actual applications that people would care about. My intent by the end of this, you should know enough that if there are problems you're currently working on, you should be able to approach them from a Bayesian point of view and craft solutions. And I'm going to give you some suggestions at the end for reading material and resources for going on and learning more. Obviously, 3 hours, there's a limit to how much depth we're going to get into, so I'll give you some pointers. Most of what I'm talking about today is based on Think Bayes, which is published by O'Reilly, but also available. There's a free version under a Creative Commons license. So if you've already checked it out or you want to check it out after the presentation, check out thinkbayes.com. So starting with Bayes' theorem, one of the things I like about Bayes' theorem is that I feel like I could have invented it. If I were left on a desert island by myself, with no resources, eventually I'm confident that I would invent Euler's method for differential equations. I did invent Kaplan-Meier estimation. I was just about 30 years too late. And Bayes' theorem, well, I'm about 200 years too late for that one. But I feel like left on a desert, I could have done it. Gödel's incompleteness theorem, I would not have come up with. So to demonstrate, starting with just definitions of what probability is, I'm going to use the notation P parenthesis A for the probability of an event, the probability that an event will occur. This is either something in the past that you don't know whether it happened or not, or a prediction you're making about what's going to happen in the future. Either way, just probability of something happening. Conditional probability of P vertical bar A is the probability of A given that B is true. So conditioned on B. And then the conjoint probability is the third line, and that is the probability of two things happening. And that's just the probability of the first one, so probability of A, times the conditional probability of B, given that A has occurred. So that's it. Those are just some definitions. Well, the third one is an actual statement of, actual law of probability. Given that, you can think about, well, conjoint probability has to be symmetric, because the probability of A and B is the same thing as the probability of B and A. So I can write it either way. The two right-hand sides there are the same thing. And if I take the two right-hand sides and set them equal to each other, I've got my equation 2. And that just says that if I want to know whether two things are happening, I can figure it out by asking, did A happen? And then did B happen conditioned on A? Or the other way around. Did B happen? And then ask about A conditioned on B. So the only difference is what order I ask the questions in, but the answer should be the same either way. If we now take the left-hand side, divide through by the probability of B, you have Bayes' theorem. So congratulations, we just derived Bayes' theorem. There's a cafe in England that has Bayes' theorem on a neon sign. The picture here is from the Wikipedia page, and I want that sign. So if any of you, if you go to that cafe, you see the sign, I would like you to steal it and deliver it to my office. Two ways to think about what Bayes' theorem is. It's very useful as a divide and conquer algorithm for going from one conditional probability to another. So if what you really want to know is the probability of A given B, sometimes that's hard. But if you can figure out the other three terms on the right-hand side, you've got the flipped conditional probability, probability of B given A, and then the probability of A, probability of B. Sometimes the right-hand side is easier to do than the left-hand side. And so you see a lot of Bayes' theorem problems where you're given the three terms on the right, your job is to compute the thing on the left. Nice, but not quite the interpretation that's usually, in this context, for Bayesian statistics, we're thinking about what's called the diachronic interpretation. Diachronic means through time. And the idea here is that you have a hypothesis, what I'm going to call H, you have some new data that becomes available, what I'm going to call D, and you're doing an update. The Bayesian update means that you start with a prior belief, which is P of H. That's what you believed about the hypothesis before you saw the data, and you're trying to compute a posterior probability, which is what you should now believe about the hypothesis now that you've seen the data. So that's when, every time I use the word update, that's what I'm talking about. Let me give a concrete example. This is one of the standard cookie problems that you see for these kinds of probability problems. Sometimes it's an urn full of marbles, but I find bowl full of cookies more appealing. So you've got two bowls of cookies. You know that one of them is 10 chocolate cookies and 30 vanilla cookies. The other one is 50-50 chocolate vanilla. You pick a bowl at random, or Fred picks a bowl at random, choose a cookie at random. It turns out to be a vanilla cookie. What's the chance that you were selecting from bowl number one? We have some intuition for this that says that, well, bowl number one is mostly vanilla. The vanilla cookie is likely, if I'm choosing from bowl number one, I'm likely to get a vanilla cookie. So given that I've got a vanilla cookie, it seems somewhat more likely that I'm drawing from bowl one. And what you're kind of doing in your head there is inverting conditional probabilities. What Bayes' theorem lets you do is do the math, quantify what your intuition is telling you. So to formulate this, H is the hypothesis that the cookie actually came from bowl one. D is the datum, the thing that you saw, the cookie is vanilla, and we're going to do that update that I described a minute ago, from a prior belief to a posterior belief. Here's what that looks like. I mentioned the P of H is called the prior. I haven't mentioned the other two terms. The probability of the data, given that a hypothesis is true, that's called the conditional likelihood of the data. That's one of the three terms on the right-hand side. The other term is the total likelihood of the data. That's what were the chances of getting a vanilla cookie under any conditions at all. Okay? We can fill in the numbers for this example. So the prior, I said I've got two bowls. I said I picked them at random. Let's assume that means 50-50. So my prior is 50% chance that it's bowl number one. The conditional likelihood of the data is relatively easy in this case. If I know that it's bowl number one, then the probability of a vanilla cookie is 3/4 because I know what's in bowl number one. The other term is the total likelihood of the data. That says what were the chances of getting a vanilla cookie if I don't know which bowl I was choosing from. In general, we have to do a little bit of math to figure that out. In this case, it's relatively simple because I can mentally take the two bowls and just combine them. And between the two bowls, I've got 5/8 vanilla cookies. So this is a case where I can compute the denominator directly. We're going to see examples in a minute where we have to do a little bit more work. But in this case, the total likelihood of the data is 5/8. At this point, you have figured out all the terms on the right-hand side, and the spirit of the good Reverend Thomas Bayes rises from the grave and comes and does the math for you. So plug everything in. The half times 3/4 divided by 3/8 works out to 3/5. So after seeing one vanilla cookie, you now believe that there is a 3/5 or 60% chance that you are drawing from bowl number one. You started out thinking it was 50-50, and if you kind of imagine a needle of belief that tips between 0 probability and 1, you're now at about 60%. So you didn't move a lot. The vanilla cookie is not particularly strong evidence, but it is evidence in the sense that you have changed your belief after seeing that datum. Okay. Since this is PyCon, we should get some Python into this Python conference. I'm going to introduce a computational framework for doing computationally what we just did by hand. The first class I'm going to introduce is PMF, which stands for probability mass function. If you've taken stats, you might be familiar with PMFs. If you haven't, I'm going to explain it in Python language. It's basically a dictionary. And it's a dictionary where you look up one of the possible outcomes, and what you get is the probability of that outcome. So you can think of it as a map from possible values or possible outcomes to their probabilities. That is what a PMF is. So we need to do a little bit of code, and this is now the point where we need to start talking about the setup. So how many of you were able to install the stuff that I sent out by email and get install test running? Oh, excellent. That's very good. Anybody brave enough to admit that you have not got it set up? Couple. Okay. Shouldn't be too bad. Here's my current plan. First of all, I strongly recommend that you don't try to install stuff while we're doing exercises and things like that, because you're going to be so focused on that that you're not going to hear a word that I'm saying. You're going to wake up 20 minutes from now with a working installation, and you'll have no idea what's going on. So don't do that. Here's the alternative. I do want you to pair up. So in fact, the tables have neatly arranged. You have been assigned partners by virtue of spatial distribution. You know who you're working with. Pair up with the person next to you. If you only have one working environment between the two of you, that's fine. And in fact, I'm pretty sure you do. If you do have two working environments, great. Do a little bit of pair programming. And what I mean by that is that one of you can have the slides up. You can be the navigator. You can be thinking about what's going on and making suggestions and spotting syntax errors. The other person can be the driver, where you're actually going to be writing the code, and your focus is kind of on the lower level details. So give that a shot. Just to give you a minute to get to know each other, I have a couple of suggestions for things that you might want to talk about. The third one is my favorite. So take a couple minutes, get yourselves set up, get to know each other. I'm going to come around and see if you need any help with any things, and we'll get going again in a couple of minutes. Okay, we should get going again. So that's it. The workshop is over. We're just going to have social hour. Good. Hopefully you now have a new best friend that you're ready to do some programming with. I will tell you my answers to 2 out of 3 of these. I had a Commodore 64 and I programmed it in BASIC, and my answer to the third one is too embarrassing. So I'll save that for after more drinks. More than 0. I should point out I have not actually been drinking this morning. There's an implication there I didn't like. Okay. Hopefully you've got a copy of the repository, which means that you've got the ThinkBayes module, which contains a bunch of the code that I use in the book, the framework that I was just talking about, the PMF and the suite class that we're going to see in a minute. Those are all in the ThinkBayes module. So if you fire up a Python interpreter, you should be able to import PMF, capital PMF, and then, and the alternative, if you prefer IPython, you can work with that. So fire up IPython, and then same thing, just go into a cell and do the import. The demo I do up here, I'll do on the command line. And so try out some of this code just to get a sense of what PMFs do. There's this slide and the next. So take a couple minutes, work through that with your partner. Let me know if you run into any problems, and I'll do the same example up front. Who asked that? Do you have something I can write on? Yes, if you have something I can write on, I'll write the URL for you. All right, sites.google.com/site/py. Nope, sorry, hang on. Maybe. No, sorry, I forget. I was thinking of the other one. So one minor note, the notes, I use the set method, but the bracket notation here does the same thing. So you can do either one you prefer. What I have here is a PMF that has 6 possible outcomes for a 6-sided die. And initially I've set them all equal to 1, which means that they all have the same probability. But those probabilities don't add up to 1, they add up to 6, which means this isn't a proper PMF. In a proper PMF, the probabilities should add up to 1. And I can make it a proper PMF by using the normalize method. The return value from the normalize method is the old total, which was 6. And if I now do d6.total, it should be approximately 1, and it is. And now I've got 6 possible outcomes, and they all have the same probability, which is 1/6, or at least the floating point approximation of 1/6. And I can do d6.random and generate a random value, and each time I roll the die, I get outcomes in proportion to their probabilities. So this is a PMF object that represents the possible ways of rolling a 6-sided die, and I showed you the normalize method and the random method. Good so far? Things working? Questions? Good. All right. So what I can do now is use the PMF class to do Bayesian updates. And the idea is that I'm going to have a PMF that contains the prior probability for each hypothesis. I'm going to do an update by looping through the hypotheses, and for each hypothesis, I'm going to multiply the prior probability by the likelihood of the data under that hypothesis. And then when you renormalize the distribution, that has the effect of dividing through by the total likelihood of the data, P of D, which was the denominator of Bayes' theorem. So this is getting the PMF class to do some of the work that we did by hand. Here's what it looks like. So if you create a new PMF object, set two hypotheses. In this case, I'm using strings to represent the hypotheses. I can do that. Anything, any type that can be put into a Python dictionary, so any hashable type, can be used to represent your hypothesis. In this case, it's just a string, so it's more like just a token that represents which hypothesis. And I'm going to start out with two equal hypotheses. So I'll have PMF, new PMF. I'm doing the same thing again. I'm showing you one version in the notes, and then I'm showing you a slightly different version up here. It's fine, they're equivalent, whichever one you like. So I've created this PMF now represents my prior beliefs about these two hypotheses. And here's how I'm going to do an update. I'm going to use the mult method to multiply each hypothesis by its conditional probability. If I know that I'm drawing from bowl number 1, then there's a 3/4 chance of getting a vanilla cookie. If I know that I'm drawing from bowl 2, then it's 50-50, and that's where I get 3/4 and 50%. So update the PMF. So I'll do a PMF. So I've done the first step of the update, which is I've multiplied each hypothesis by its likelihood. And what I have here is not quite a posterior distribution yet because it's not normalized. Notice that the probabilities don't add up to 1. When you normalize the PMF, you're dividing through by P of D, the total probability of the data. So PMF. And what it prints is the normalization constant, which is the total probability of the data, which is my 0.625. And now, if I display it, I have probability of bowl 2 is 0.4, probability of bowl 1 is very, very close to 0.6, which is what we got before, which is good because we were hoping this would come out the same as before. Good? Questions? Yes, sir. You have a different result. Check with your partner and see if you can figure it out. Part of the pair programming thing is often your two heads will figure out what went wrong. And if not, one thing that can go wrong is if you update one of the hypotheses and then normalize, and then update the other hypothesis and then normalize. That will not be the right thing. But I see nodding and smiling. I saw that sort of sheepish grin of, oh, I realize I've done something incorrect. Okay. Good. Okay, so 0.6, which is what we like. All right, I have an exercise for you. So suppose that you chose from that random bowl, same bowl, you go back in and draw another cookie, and it turns out to be a chocolate cookie. I want you to do another update based on the second piece of data. So the posterior distribution that you just computed is going to become the prior for the next update. And if you like, let's keep it simple. Let's pretend that the proportion of cookies in the two bowls does not change. So forget about the other cookie that you took out. If you want, you can figure it out. It will be a slightly different number, but just to keep it simple, let's pretend that bowl 1 is still 3/4 vanilla, bowl 2 is still 50-50. So with all of these exercises, one of the things I'll do is while you're working, I'll be showing a solution up here. So anytime you get stuck, you can cheat by just looking up here. The other, when we start working with the files in a minute, you'll see that the solutions are also in the repository. So if you get stuck, don't feel like you have to stay stuck. Feel free to cheat. I mentioned if we're drawing from the same bowl again, so we've already taken one vanilla cookie, now we're drawing a chocolate cookie. The second update is going to be to multiply by the conditional probability 0.25. And that's saying that if it's bowl number 1 and I got a chocolate cookie, there's only a 25% chance of that outcome. If it's bowl number 2, the chance of a chocolate cookie is 50-50. Renormalize the distributions and then print the results. And now what we see is that we've actually changed our minds a little bit. The posterior probability for bowl 1 is now 0.43, and bowl 2 has jumped up to 0.57, or almost 0.58. Okay. So having seen one chocolate and one vanilla, we now are somewhat inclined. It's kind of weak. We haven't moved the needle very far, but we're somewhat inclined to think it's probably bowl 2. That is it for cookie problems. Any questions so far? Yes, sir.
If you were going to try to account for cookie taken out,
Mm-hmm.
how would you do that? Because it could be either one. Would you almost have to multiply?
Kind of. Yes. So the question is, what if you do want to keep track of the cookies and keep track of the counts that you've seen so far? What you would have to do is you would have two hypothetical worlds. If it's bowl number 1, then I would decrement that cookie from bowl number 1 and then compute the subsequent probabilities. At the same time, I would have a different hypothetical world where it's bowl 2, and I would be pulling cookies out of bowl 2. And those two worlds would contradict each other. But that's all right. You're kind of, you think of them as separate universes. If I'm in universe 1, I do all the computations. If it's universe 2, same thing.
And do you average those probabilities by your prior belief, which one bowl it was?
And then the question is, do you average the priors by which bowl? So you're gonna start out with equal priors, the 50-50, and then your two universes are going to diverge. Let's come back to this one. It might. Sorry, no, I'm not explaining this well. It will end up with one posterior probability about what you believe about the actual universe that you're in. Let me punt this one for now. I'm going to come back during a break and try to do a less confusing job of it. Okay, so moving on from cookies, we're going to get to dice. From dice, we're going to get to trains, and then German tanks. That's where we're headed. Imagine that I have a box of dice, and if you've ever played Dungeons and Dragons, you know what I'm talking about. You have a 4-sided die, a 6-sided, 8-sided, 12-sided, and 20-sided die. So I pull out a die, I don't let you see what it is, I roll it, and I report to you that the outcome is a 6. And your job is to guess which die it was that I rolled. Okay? How we're going to do this, I'm going to introduce a new class that's called a suite. You can see from my UML diagram that a suite inherits from PMF. So everything that you just did with PMFs, you can also do with suite, but a suite has one additional function, which is actually two additional functions. One of them is an init method, where you can give it a list of hypotheses, and it will start out with equal probabilities for each of those hypotheses. So by default, you get a uniform distribution where every hypothesis has the same prior probability. You can override that for other prior distributions. Here's the centerpiece of the whole thing. Yes, sir?
When you say hypothesis, do you mean the keys in the dictionary, essentially?
Yes. Okay. The hypotheses I'm talking about are the keys in this dictionary. Yep. Here is the Bayesian update. What we just did, kind of manually, this function now encapsulates. This says if I've got a suite of hypotheses, somebody comes along and gives me a new piece of data, I'm going to loop through all the hypotheses, which are the keys or values in the dictionary. Yeah, that. And then for each one, I'm going to compute the likelihood of the data under the hypothesis, multiply the hypothesis by that likelihood that I just computed, and then renormalize the distribution. So suite provides this framework. What it doesn't provide is the likelihood function. That's your job. Likelihood is an abstract method in some sense. Python doesn't really do abstract methods, but you can kind of make abstract methods. So the parent class provides update. What you do is you define a child class that inherits everything from suite, and you provide the likelihood method. So the first example we're going to do is a class called dice that's going to provide the likelihood method that we were just talking about. So let's figure out what that is. If I don't know which die it is, I roll a 6. If it is actually a 6-sided die, what's the probability of that outcome? 1 in 6. If it's a 10-sided die, what's the probability of rolling a 6? 1 in 10. If it's a 4-sided die, what's the probability of rolling a 6? 0. Okay. So you know the likelihood function. All you have to do is fill it in. And that is your next exercise. If you go into the repository, you'll find a file called dice.py. It has everything you need to solve this problem except the likelihood method. Your job is to fill it in. Okay. Just to get a sense of how things are going, how many of you were able to write a likelihood method that you think is correct and you're getting some results out of it that are making sense? Oh, okay. How many people would like another minute or two to keep working on it? All right, one more minute, and then I'll interrupt you. Again, if you want to cheat, go ahead and look up here. I've got a solution.
Yeah. So is this likelihood function just basically like the 9?
Okay, I just got a great question that I want to repeat, which is, while you are writing this likelihood function, you don't have to think about any of this Bayesian update stuff. You have this compartmentalized view of the world that says, if I tell you which hypothesis is true, all you have to do is compute the likelihood of the data. So in this case, each time this function gets executed, you're being told it's a four-sided die, and the outcome was 6. What was the probability of that? And so you would say, well, if the hypothetical number of sides on the die is less than what the outcome was, that can't happen, so the likelihood of that datum under that hypothesis is 0. Somebody comes back and says, okay, well, what if it was a 10-sided die and you got a 6? Then you would say 1 over 10. And that is what that does. And similarly, if it was a 15-sided die or 17, whatever it is, it's just 1 over m. Okay? Does it make sense what the likelihood function is? And now, in the same way that the spirit of the good Reverend Thomas Bayes comes from the grave and does all the math for you, he also does computation. So if we now run this, the outcome after seeing 1, 6 is that the four-sided die now has posterior probability 0. That makes sense. That hypothesis has been ruled out. So the posterior is 0. The 6-sided die is looking quite likely, about 39%. I'll switch over to my slides because they're a little bit more readable. There we go. 6-sided die is looking very likely. The 8-sided die a little bit less. 12 a little bit less, and 20 a little bit less. The fact that we saw a low number suggests that it might not be the 20-sided die, which is a little bit non-obvious. The 20-sided die has certainly not been ruled out, but it's less likely than the 6. Make sense? So that's what the posterior looks like. If I take the same die and roll it a few more times, one nice thing about this framework is that multiple updates, very easy, just put it into a loop. So keep the 6-sided die, keep the 6 that we already rolled, and now we're also going to roll an 8, 7, 7, 5, 4. So now we've rolled this die 6 times. We've never seen a number that was any higher than 8. Which die do you think it is? Probably 8. 6 has been ruled out. 4 has been ruled out. 12 and 20, they're still possible, but it's looking less and less likely that I would roll a 20-sided die 6 times and never see anything bigger than 8. So what's your intuition? I'm curious to know, how confident are you at this point that it's the 8-sided die? You've rolled 6 times. These are the outcomes. What do you think? 80%, 70, 90, 92? Now, I have to admit, I did encourage you to cheat, so I have only myself to blame. Here's the actual posterior distribution. As I said, 4 and 6 have been ruled out. 8 is looking very likely. The wise guy who said 92% is correct. And 12 and 20 are much lower probabilities. For me, at least, the probability for the 20-sided die is lower than my intuition indicated. It's actually, at this point, quite unlikely. Now, all of this is subject to change. I've rolled this die 6 times. Let's say that I roll it one more time and I get a 15. All of a sudden, your beliefs would change radically. The 20-sided, let's see, 4, 6, 8, and 12 are now out. And the 20-sided die now has a posterior probability of 1. Okay. So that is the dice problem. Let me just see if there's anything else I was going to say about that. No. Questions? Good so far? All right. Should we take a break? Where are we here? We are at 9:48. Actually, I'm going to postpone the break just a little bit because we're making good progress. I want to do one more problem before we do the break. We'll do train spotting first. That's a little cruel. I sort of showed it to you and then took it away. Coffee break? No. Train spotting problem. This, by the way, has nothing to do with heroin. This is train spotting used to be a legitimate hobby where you would go down to the rail yard and you would read the numbers off the locomotives, and sort of like collecting cards, you would keep track of what you had seen, or birds. If I've seen a red-throated warbler. I don't know. So let's imagine that you are a scout for a rail carrier, and the competing company, you want to know how many locomotives one of your competitors is operating. And from background information, you've got it narrowed down. You're pretty convinced that they have more than 100 locomotives. You're pretty sure they don't have 1,000. And just for a starting place, let's say that you think it's equally likely. Anything in that range would be equally unsurprising to you. So uniform prior distribution between 0 and 100. You go down to the rail yard and you spot train number 321. And you happen to know from corporate espionage that your competitor numbers their trains from 1 to n, where n is how many trains they have. So this is a little bit of an artificial problem, but I'm going to explain why the rules are the way they are in a minute. What you want to do is figure out your posterior belief. Having seen train number 321, now how many trains do you think your competitor is operating? Okay. So your job is to load up train.py and fill in the likelihood function. Same thing as before, don't think about the Bayesian framework, just think about the likelihood. So if you were in a box and somebody slid 2 pieces of information under the door, data, hypothesis, they say, if the competitor had 550 trains, what would be the chance of seeing train number 321? And you're going to write the likelihood function for that. So try it out, train.py, fill in an answer. This is what the prior looks like. This is just a uniform between 0 and 1,000. So if you feel like I played a trick on you, that feeling might not be unwarranted. The logic here is exactly the same. If I think they only have 200 trains and I see train number 321, that hypothesis can't be true. So that's the first clause there. And if I think they've got 500 trains and I see any train in the range from 1 to 500, then I would say, well, the chance of that is 1 over n, or 1 over the hypothetical number of trains. So this likelihood function is exactly the same as for the dice. The only difference is that I have more dice. In some sense, I have a 100-sided die, a 101-sided die, all the way up to a 1,000-sided die. But the logic is the same. And if you run the program again, if you haven't run it yet, think for a minute about what you think it'll look like. And then run it. Fortunately, my laptop is so slow that you're going to have at least 5 seconds to think about it before it pops up. That makes sense? So we expect the left-hand side of this makes sense, that everything from 320 on down has been ruled out. Everything from 1,000 on up has been ruled out, or it was originally. And then the curve itself is a 1 over n curve. It's kind of 1 over n that's been truncated at both ends and then renormalized. And that's why it's kind of stacked up like that. So one funny thing about this is if somebody now came to you, so you went to the rail yard, you saw train number 321, and they said, what's your best guess about how many trains your competitor is operating? What would you guess? 321, which seems a little counterintuitive. And this is one of the things to think about when you generate a posterior distribution. The posterior tells you all the information that you have about the world after having seen the data. But there are a lot of different ways that you could now summarize that distribution. If somebody actually asks for your best guess, what they sometimes mean is, what's the value that you think is most likely to be true? So if it's like a contest where you have to guess the weight of a wheel of cheese or something, you would want the guess that has the highest probability of being correct. In this case, that would be the 321. And that's called the MAP, the maximum a priori probability is 321. Yes, sir? Good question. Okay, so there's this lower bound of 100, and that doesn't seem to have come into the calculation at all. But again, put on your Bayesian blinders. Forget about the problem. When you compute the likelihood function, all you know is the hypothesis and the data. In this case, if they have 500 trains and you saw 321, then the answer is 1 over 500. And the 100 doesn't come into it, which is a little bit maybe counterintuitive. What it says is in my prior, the lower bound didn't matter very much. If the lower bound of my prior had been 200, my answer would have been exactly, the posterior would end up being exactly the same. Yes?
But if you saw train number 50, that lower limit would play a significant role.
Ah, that's a great question. So what if my lower bound in the prior was 100, and I went and I saw train 50? No, that's all right. Yes, but in that case, the lower bound of my prior would also be the lower bound of my posterior. So you're right. In that example, the lower bound of the prior would still matter. Math would work the same. Yeah, we can do it. So the question on the table is, if my lower bound is still 100, but instead of seeing train number 321, I see train 50. Let's run that again. Correct. If you couldn't hear that, it's just a reminder that that lower bound, the 100, that's what you think is the lowest number of trains your competitor is operating. It's not to say that the trains are numbered from 100 to something else. So if that was a point of confusion, I'm glad you cleared that up. And then just, so here's the example where you saw train 50. The lower bound started out as 100 and it's still 100. Because you haven't seen a number bigger than 100, so that hypothesis is still viable. And so this is similar to what we saw before, but it includes more low values. Yes? This graph would not change for any value under 100, correct? Good. All right. Good questions. Thank you. So just to back up, we were talking a little bit about how to summarize, and we said that if you're trying to guess the weight of the wheel of cheese, you would say 321, but that's probably not, that's not the right cost function. If you want to think of it as like a cost-benefit analysis, if you're scouting your competitor, you probably want to know something that's about right on average. And so one alternative is to take a posterior mean, so you can compute the mean of the posterior distribution. Another possibility, maybe you go to your boss and you say, I'm not sure exactly how many trains they have, but I can give you an interval, and I think there's a 90% chance that the correct value falls in this interval. So we'll do both of those. I've got a couple of functions that are built into the suite class. Mean computes the posterior mean. Maximum likelihood gives you which value has the maximum likelihood in the posterior. And the credible interval is the Bayesian term. You might have heard of confidence intervals in the context of classical statistics. Credible interval in Bayesian statistics is a very similar idea. It's an interval that contains 90% of the probability. And let's compute those things. And I forget, is this already in? It is not. So if you will add this to train.py, let's put those in. And I notice that in my slides, I'm currently using the Python 2 syntax without the parentheses. But we are now in kind of Python 3 compatible world, so do include the parentheses. And the suite is called suite. Yes. Okay, so here's the code. I just copied it in from the slides. So it's going to do mean, maximum likelihood, and then credible interval. Here's the posterior. I switched back to the case where it's train number 321, because that's the one that you're probably working with. And here are the results. 597 is the posterior mean. Somebody asked me, is that the probability weighted mean? Yes, it is. And 321 is the most likely value. And the interval is 339 to 945, okay, which is pretty wide. I started with 100, 1,000. Now it's 339, 945. Having seen one train, I haven't narrowed it a great deal. And that makes sense. It's a small amount of data. It shouldn't change my beliefs enormously. But the same thing that I said with the dice problem is also true with the train. If you spot more trains, you can just add more updates to the file. So let's make up a couple more numbers. Somebody tell me. I go down to the rail yard. I see another train. What number is it? 655. Excellent choice. So in your head, think for a second about what things will look like. You've seen train 655 and 321. What's the posterior going to look like? And I will run it. That is what that looks like. Yes, sir.
So being that 321 is most likely trade to the even that you're going to see, right?
Yep.
How come the 90% credible interval starts after that?
Ah, good question. Tell you what, can I back up? I want to just do this example first, and then I'll go back to answer your question. So I saw, what was it, 655? Is that what you said? So everything below 654 has been ruled out, and this curve now drops off like 1 over n squared, because I multiplied by 1 over n and then again. So I've taken 1 over n squared again, truncated it, and renormalized it. And that's what that looks like. So it's getting narrower and narrower, which means that I'm more and more certain about how many trains they have. And you can see that the confidence interval is getting smaller and smaller, and that's good. Now, to answer the question I got a second ago, let me just go back to the original scenario. And the question was why my confidence interval does not contain the most likely choice. The confidence interval, it's a 90% confidence interval. I chop off 5% of the probability from the left and from the right. And so the interval will go from about here to about there, but it doesn't, in this case, actually contain 321. That's a little bit of a quirk. There are actually lots of 90% posterior intervals. You could choose any set of values that adds up to 90%. So if you wanted, you could do the first 90% and lop off 10 at this end. And for some applications, that might be a preferable choice for that credible interval. But it's a good question. Okay. I want to wrap up trains, and then that coffee break that I promised a minute ago will actually happen. Two things I mentioned, if you want to loop through more trains, you can. The reason that I did this example is that it turns out that, yeah, it's got some nice properties. So we practiced a little bit. It's a nice example that uses sparse data. One of the things that Bayesian methods are good for is if you have just a tiny amount of data, you can wring the maximum amount of information out of them. The posterior represents everything that you know about the world after having seen that data. The other reason I wanted to do this problem is that it's kind of a real problem. The German tank problem actually came up during World War II. Every time the Allies captured a German tank, they would take it apart and they would look at the serial numbers on all the parts. And they would do statistical analysis on the serial numbers, which is kind of what we just did with trains. And in particular, the wheel molds were numbered. They were issued in blocks of serial numbers. So a given factory during a given month would have a block of serial numbers that was 100 wide. And what we didn't know was how much of that block had been used. So we knew it was somewhere between 1 and 100. It was kind of equally likely to be any of them. And anytime you found a serial number, you could do an update based on that. So during World War II, the Allied forces were actually doing that analysis. After the war, they got the records and were able to compare their statistical estimates with reality. And it turned out the Bayesian methods had been remarkably accurate and much more accurate than what they were getting from conventional espionage. So the spies were telling them numbers that were like 1,000 tanks per month, and the reality was about 200 tanks per month. And the Bayesian estimates were just about right. So this is a nice example where in a little bit over an hour, we've gone from kind of toy problems with cookies and things like that to an analysis that's legit. This is a real world problem that had life and death consequences. Let me just see. Yes, I'll pause for questions, and then we will take that long postponed coffee break. So now you don't want to ask a question because everyone in the room is going to hate you. All right, let's take a break. You can ask me face to face if you want. I realize now that I made a tactical error by not announcing how long this break would be. Uh, but I'll start again in about 2 minutes, and hopefully everyone will be back. Let's get going again. Next problem up, I promise, is not the same as the train problem and the dice problem. This one's actually a different likelihood function. So this comes from David Mackay's book, which is where I learned about Bayesian statistics. It's one of the books I'm going to recommend at the end, so I'll give you a pointer to it. But this is one of the problems that he presents. When the euro coins were first being introduced, the Belgian euro coin for some reason attracted attention because it seemed, somebody did this experiment, if you spin it on edge and wait for it to fall over, it seemed like it was falling with the head side up more often than 50-50. So somebody with too much time on their hands spun it 250 times, came up 140 heads, 110 tails. They went to a statistician who computed a p-value. If you are familiar with p-values, he said the chance of seeing an outcome as lopsided as that, if the coin is actually fair, is quite small. It's about 7%. So classical statistics would tell you that this seems like a suspicious outcome. The question is, from a Bayesian point of view, do these data, the 140-110 split, do these data provide evidence that the coin is biased rather than fair? So we're going to do this in 2 steps. The first thing we're going to do is to try to estimate what is the probability that this coin will land heads side up. And then we'll come back to the more general question of what we should believe about the coin after seeing this evidence. Now, one thing that's a little bit confusing is that this thing that I'm going to call x is the probability that the coin will land head side up. If you think of that thing as being a probability, your head is going to explode in about 10 minutes. So don't do that. What I want you to just think of this as being a physical characteristic of the coin. This coin has a weight and a diameter and a thickness, and it has some probability x of landing head side up. And we're going to try to estimate what that value is. We're going to try to estimate what x is. But we're going to have probabilistic beliefs about x. We're going to say things like, I think there's a 50% chance that x is 0.6. That will be confusing. So brace for it. Okay, as I said, we're going to do this in 2 steps, estimation and then hypothesis testing. The first step is estimation. We're going to use the suite class again. We're going to have a new class called euro. Again, it's going to inherit from suite. So you get update free. Your job is to write likelihood. And here's what I want you to figure out. So we're going to have a class called euro. It inherits from suite. We're writing a likelihood function. Somebody's going to give you the data and the hypothesis. Data is going to be a string. It's either capital H string to represent heads or capital T for tails. And hypo is the hypothetical probability, the hypothetical value of x. And so it'll be a number, and you can think of it as an integer or a floating point value, doesn't matter, but it'll be in the range from, I guess, 0 to 100. I don't know why I said 1 there. So from 0 to 100. And your job is to modify euro.py to fill in this method. Okay, I'm going to go over a solution. If you're still working and you don't want me to give away the answer yet, ignore me. If you're stuck or you want to see what I did, feel free. So the first thing I did, somebody gives me hypo. Hypo is a value from 0 to 100. I did that because we tend to think of probabilities as 0 to 100, but for mathematical purposes, 0 to 1 is the way to go. So I convert my hypothesis to a probability. And now I said this during while you were working, but just to repeat, the nice thing about the Bayesian blinders is that you don't have to think about the big complicated problem. You are in a little tiny box and somebody comes up to you and says, here's P, the probability of getting heads, and it's 60%. And the outcome was heads. What was the probability of that outcome if the hypothesis is true? And you scratch your head for a minute and you think, is it really as simple as it seems? Yes, it is 60%. And the flip side is if they tell you that it's 60% and they tell you that you got tails, then that's 40%, which is just p n 1 minus p in the code. And that's it. That is the likelihood function. Once you've done that, your job is over. All the hard thinking is done, and you can run it again. euro.py. And while my laptop is working as hard as it can, both squirrels calculating as fast as they can, you can think about what the posterior should look like. So this is after I've seen one heads. Well, we can think about what the endpoints look like. If the hypothesis was 0, the hypothesis is that this coin cannot yield heads, and I see heads. That hypothesis has been ruled out. And so the posterior probability is 0. If the hypothesis was this coin always yields heads, and I see heads, well, that's a very likely outcome, and so that actually is the most likely posterior hypothesis. And it's a straight line in between. The straight line comes from the mathematics, which is that the probability of the outcome is proportional to your hypothetical probability. So after having seen one coin toss, we have a linear relationship between these two. If you go back to the slides, we can think about what it's going to look like with more data. So there's my solution. This is the prior distribution. This is what was in the code that I gave you. So this is a uniform distribution from 0 to 100. After doing one update, we have a straight line. And now the question I want you to think about is, what if we spin it again and we get heads again? Obviously, you can run your code. Again, if you just put it into a loop or do 2 consecutive updates, either one is fine. You'll see what the posterior looks like, but also think about it. So one update got me from a constant to a linear function. I'm going to multiply by p again. What's the posterior going to look like? So the low values, everything from 20 on down, is looking less and less likely. If this thing has a 1 in 10 chance of producing heads, then the 2 heads that I just flipped would have only a 1 in 100 chance. So those are looking less and less likely. The high end of the spectrum is looking more and more likely, and I've got something there that kind of looks like it might be a parabola. And in fact, mathematically, it is a parabola. In general, the solution to these with the uniform prior are going to be polynomials. Questions about 2 head flips? So I flip or spin, however you want to think about it. Suppose I flip it one more time and this time I get a tails. What effect is that going to have on the posterior? Again, think about it. Maybe consult with your opponent, partner. And then run the code and see what it looks like. So this is what it looks like after seeing 1 tails and 2 heads. We already knew this couldn't be true because we had seen a heads. Now we know that this can't be true because we've seen a tails. And this actually turns out to be a cubic curve. Anybody have a guess about where the peak of that curve is? What is the MAP, the maximum maximum a posteriori probability? It is at 2/3. You've seen 2 heads and 1 tail, so if somebody asked you what's your best guess, you would probably say 2/3. And Bayes would agree with you. But one nice thing that Bayes is doing for you is not just giving you a single point estimate about what you think the probability is, it's giving you the whole distribution. And that distribution gives you a sense of the best value, but also how confident you are about that value. Having seen just 1 tails and 2 heads, this distribution is still quite wide, meaning that you are not very confident about what X is for this coin. If you run more data, so let's say that you run it 10 times, you get 7 heads and 3 tails. Same thing that we've seen a few times, you can do the update like this. This is what it looks like after 10 flips. So the center of this now is at 0.7. The center has not moved very much, but the distribution has become narrower. That narrowness is a measure of how certain you are about X. And if you generate more data, like 250 flips, so now this is the example that we were given, 140 heads and 210 tails. The posterior distribution looks like that. So quite a bit narrower. The peak, again, is at the observed proportion, which is 0.56-ish. And it's kind of narrow. We're pretty sure that if it's anything bigger than about 65, this outcome would be very unlikely. And if it's anything less than about 45, it's quite unlikely. And again, we could compute a credible interval that contains 95% of the posterior mass, or whatever fraction we want. So same question that I asked before about summarizing the posterior suite. One question you might be tempted to ask, but which you should not ask, is what is the chance that this coin is fair, 50-50, in the posterior distribution? You could do that. You could look it up. You could say, in the posterior suite, what's the probability of the 50% hypothesis? But you're looking up a very specific value in a distribution that's actually kind of like a continuous distribution. The value that you get is going to be meaningless. In this case, it's 0.021, but if I take this range from 0 to 100 and I chop it up into finer slices, so instead of the integers, if I did half or a quarter or a tenth or whatever it was, this number would change depending on arbitrary choices that I make. So this is not a useful way to describe the posterior probability of a 50-50 coin. We can do what we did before, which is the maximum likelihood. And again, what you get is the 56%, which is the observed proportion. You can get the posterior mean. In this case, it's also very close to 56%. This is a nice symmetric distribution. So the peak and the mean are pretty close to each other. You can get a credible interval. In this case, the 90% credible interval is between 51 and 61. Okay. Now, I want to make one point getting back to, I mentioned confidence intervals. This is one of the things that is complicated in classical statistics and remarkably simple in Bayesian land. You're always tempted when you compute a credible interval, you would like to be able to say, is there a 90% chance that X falls in that interval? In classical statistics, this is an endless debate. If you ask statisticians to explain to you what a credible interval is, you are in for a long afternoon. Just don't. The nice thing about Bayesian, you are treating X as if it is a random quantity. It's a little bit funny to do that because, as I said, it's a physical characteristic. It'd be a little funny if you asked me for the weight of a coin, and I said, well, that's a random number, and it's a random number in this range. You would say, wait, it's a weight, or Planck's constant. If I told you that Planck's constant, or the weight of an electron, is a random quantity, you would think that that was a funny thing to do. But if you're willing to bite that bullet, the nice thing that you get from it is that, yep, you can think of 51, 61 as an interval that has a 90% chance of containing the right answer, and you can use that for decision-making processes. I mentioned cost-benefit analysis or anything like that. There is a price that you pay for this, which is that the result that you get at the end, the posterior, depends on the prior. And the prior is subjective. Reasonable people could disagree about what the right prior is. So in this example, I deliberately chose something that kind of doesn't make sense. If I show you something that's an actual coin, the Belgian euro coin, and I tell you I'm going to spin it on end and I'm going to count how often it comes up heads or tails, you would expect it to be pretty close to 50%. You might believe, just based on what you know about physics and coins, you might believe it could be 51 or 49, sure, that's possible. 60, maybe, that would be kind of a weird coin, but maybe 40, yeah, okay. 90? I doubt I could make a coin that would fall one way 90% of the time. If I made something that was like really obviously lopsided, like a coin that was concave, then yeah, okay, I believe that. But a normal looking coin that is not obviously totally off weight, a uniform distribution does not seem like a reasonable choice. So just as an alternative, we could try something like a triangle prior. So the blue line is what I used before. The blue line says anything between 0 and 100, equally unsurprising to me. The green line is a little bit more like what I actually believe about coins, that the values in the middle are much more likely than the extremes. And in this case, I'm saying, look, I don't think you can make a coin that will always fall the same way, or heads or tails. Okay? So this is closer to what we really believe about coins. We could still debate about whether it's the right prior. Fortunately, we don't have to have that debate. These are the two posterior probabilities for those priors. Okay. After having seen 250 coin tosses, the blue and the green lines are all but identical, at least as far as we can tell from plotting it. Now, they will never be the same. Mathematically, if you start with different priors, you will end up with different posteriors, except in special cases. But if you are having a debate with somebody and you converge to the point where your beliefs look like this, you could call off the debate. You could agree at this point that the difference is small enough that we don't care anymore. And that is one of the nice things about this analysis. If you get enough data, you mostly don't have to agree about the priors. Eventually, the data will swamp the priors, and reasonable people will converge at least close enough for practical purposes, with one exception. If you give a hypothesis a prior probability of 0, no amount of data will ever change your mind. And you can see that mathematically because we're always taking the prior and multiplying it by a likelihood. And anything multiplied by 0 is 0. And you can also think about that intuitively. If you are convinced that something cannot possibly be true, no data will change your mind. So there's a heuristic that people sometimes recommend that's called Cromwell's rule. And the idea is that you can pick any prior you want, just not 0. You can have 10 to the minus 100 or 10 to the minus 1,000, any extremely small number. If you think, have UFOs ever visited Earth, or do people have ESP, or whatever hypothesis you think is not true, just give it a very, very small prior. Eventually, I could persuade you with data. But if you go all the way to 0, then I'm done. This comes from Oliver Cromwell. The reason it's called Cromwell's rule is this sort of overwrought, I beseech you in the bowels of Christ to think it possible that you may be mistaken, which is good advice for Bayesians, and also, I think, generally good epistemological advice. All right, so just to summarize what we've done so far, you form a suite of hypotheses that represent anything that could possibly be true. You choose a prior distribution. It's subjective, but live with it. You compute likelihoods. Once you get to steps 3, again, the spirit of Thomas Bayes comes and does all the work for you, and then you've got your posterior beliefs. But I've done a little bit of a bait and switch here. I started with this question: do these data give evidence that the coin is biased rather than fair? And what I did was I estimated the probability, but I have not done this, which is more like a hypothesis test. If you know classical statistics, this is a hypothesis test. So I'll give you the Bayesian version of hypothesis testing. And it's based on this idea of evidence. We would say that a piece of data, D, is evidence in favor of a given hypothesis if any of these are true. They're all equivalent. So if my posterior is greater than my prior after having seen this datum, then that datum is evidence in favor of H. And that will be true if the data are more likely under H than they are under not H. That little twiddle there means not. And if you have a particular hypothesis that you like, then not H is all the other hypotheses. Okay? And then just taking this one and rearranging a little bit, we can write this ratio, which is called a likelihood ratio. It's also called a Bayes factor. And it is the likelihood of the data under your hypothesis compared to the likelihood of the data under the alternate hypothesis, not H. Bayes factor, it's a measure of the strength of the evidence. If that number is greater than 1, then the evidence are in your favor. The data are in your favor. If it's less than 1, they are against you. And the magnitude is how strong that evidence is. We'll see an example in a minute. So now let's get back to the original question. I started with 2 hypotheses. Either the coin is fair or the coin is biased. And I need to compute that likelihood ratio, the Bayes factor. So I need to be able to compute the probability of the data. In this case, again, the data are the 250 outcomes, the 140, 110. Under the fair hypothesis, that's easy to compute. So under the fair hypothesis, the coin has a 50% chance of yielding heads, and it's easy to compute the probability of any given outcome. Under the biased hypothesis, I have some more work to do, because if you tell me that you believe that a coin is biased, you have underspecified the hypothesis. There are a lot of things you might mean when you say that. And I can't compute the second term until we get more specific. So you can think of this as a little bit like a barroom bet. You know, you've been I think that coin's biased. I think that coin's fair. Well, let's bet on it. Well, in order to make it a bet, we have to figure out the terms of the bet. So here's one way to specify what B means that is a total cheat. You can't do this. Okay? What you could do is you could look at the data and you could say, well, in the data set, it comes up to be about 56%, the 140 out of 250. So that's my hypothesis. When I say biased, I mean 56% heads. Now, good, let's compute posterior probabilities. This is a cheat in part because you can't look at the data in order to formulate your hypothesis and then use the data again to update your beliefs. Each datum, you can only use it once. It's like cashing a check, you're done. The other one is, if this is the way to test whether a coin is biased, then every coin is biased. You would always, what you actually observed will always be very likely under this hypothesis. So this is not legit. We need rules. Rule number 1, you have to choose your hypothesis before you see the data. The other is, you can have a range of hypotheses. You can say, I think the coin is biased, but I don't know by how much. You could say, I think it's between 60 and 70, or I think it's between 51 and 80. Something like that. You're allowed to have a range of hypotheses, but if you have a range of hypotheses, then I'm going to average the likelihood across your range of beliefs. I'll show you what that looks like. This is, by the way, this is the same rules as playing roulette in a casino. You have to place your bets before the outcome is known. Placing your bets after the outcome is known is officially not legal. And the other is you can bet on as many squares as you want, but the return on your investment will be the average across all your bets. So some will win and some will lose, and you get the average. Seems fair. Here's what that looks like as code. if you give me a suite that represents your definition of biased, I'm going to integrate over it. I'm going to loop through each of the hypotheses, compute the likelihood of the data under each hypothesis, and I'm going to compute a total likelihood or an average likelihood that is a weighted average of the likelihoods weighted by how much you bet on each of the roulette squares. Okay? So again, F is the hypothesis that the coin is fair. B is the hypothesis that it's something else. I'm going to start with one definition of B, and then you're going to have a chance to play with it. I'm going to start with something very simple that just says it's biased, so not 50%, but anything else between 0 and 100, equally likely. Okay. So here's what that looks like. I'm going to create a suite that's called fair that represents the fair hypothesis, and it only has one value in it, 50%, and I'm certain that that's what it is. The biased hypothesis has all the values from 0 to 100 except 50. Okay. And now I'm going to compute the likelihood of fair and the likelihood of biased for each of those suites. Okay, so I'm going to spin the roulette wheel, see what the result is, come up with this ratio. That ratio is the Bayes factor. Remember again that it is, if it's greater than 1, then the biased hypothesis is more likely. If this is less than 1, then the fair hypothesis is more likely. So take a look. I've got some code for this in euro2.py. Take a look through it. You're going to have to read that code a little bit because I've changed some things around, and run it. Take a look at the results and interpret what those results mean. We'll go over it in a couple of minutes, and if you have questions, I'll come around. Again, if you're making progress and you don't want to be interrupted, ignore me. If you want to hear what I'm explain a couple things, I will. So this is the new likelihood function. I've changed the representation of the data. It used to be a string that was either heads or tails. Now it's a tuple that contains the number of heads and the number of tails. I did that partly for efficiency and also just to show off a different way to do this problem. Instead of doing an update every time you see a coin flip, you can do one update with the total outcome, the 250, the 140 and the 110. And that's by doing the probability of heads raised to the number of times that heads occurs times the probability of tails raised to the power of how many times tails occurs. And that's the binomial distribution, if you're familiar with that. So if that's familiar and it makes sense, great. If you haven't seen that before and it's black magic, that's all right. Just think of it as black magic. It's an efficient way to do the whole update all at once. Let's take a look at the results. If you run this, euro2.py, We're going to get the likelihood of the data if the coin is fair, the likelihood of the data if the coin is biased, and the ratio of those two things is the Bayes factor. So if the coin is biased, we've got a really, really small number, which means that this particular outcome is unlikely to have occurred because there are so many outcomes. But actually, we don't really care how small that number is. We only care about the ratio. So ignore all the digits except the first two. The likelihood, if it's biased, is about 2.6 something, and compared to 5.5. So this is actually more likely under the fair hypothesis. And so the ratio is less than 1, which means that it's against the biased hypothesis and in favor of the fair hypothesis. That's a little bit of a counterintuitive result. When we started, we said, it's suspicious, it's weird that we saw so many heads. And that is unlikely to have occurred if the coin is fair. Nevertheless, what this is telling us is that all things considered, these data are evidence in favor of the fair hypothesis. You should be more inclined to believe that the coin is fair after seeing these data. Yes?
But you have to define the biased distribution before you do the calculation, right?
That's right. I have to define what biased means before I did this calculation. And in this particular example, the definition that I chose for biased is kind of a funny one. I said equally likely between 0 and 100. And in real life, if you tell me that you think a coin is biased, that's probably not what you mean. So I tilted the scales a little bit against, let's say, if you think of it as me versus you, I think it's fair, you think it's biased. I cheated a little bit by sticking you with a bad definition of what biased means. You now have a chance to get even with me, which is go into euro2.py and change the bias suite to whatever you think is a better definition. If you think a coin is biased, build a suite that represents that claim and do this computation again. I put one version of this in the notes if you want to use mine. This is the triangle prior that I had before. So this is saying, I think the values in the middle around 50 are likely, the values at the extremes are 0 and linear. And this moves the Bayes factor a little bit, but you can try out other versions if you want. Take another minute, do your version. I'll go over a couple of examples in a minute. Okay, let me look at a couple of examples. This is the triangle prior that I was just telling you a minute ago. This is a more reasonable definition of what biased might mean to you. And here's what that outcome looks like. The likelihood under the fair hypothesis has not changed. The likelihood under the biased hypothesis has increased a little bit, and that's because I've taken some of the losing bets and I've given them less weight. And the ones that are closer to the middle that were the good bets now have higher weight, so the average is better. The Bayes factor is still less than 1. So this data is still evidence for a fair coin, but it is now weaker evidence. The closer you get to 1, the weaker the evidence, the bigger the magnitude, the stronger the evidence. So, all right, maybe let me tweak the biased hypothesis. Let me get rid of the really dumb bets. I think anything less than 25 should be ignored. Anything more than 75 should be ignored. And triangle shaped in between. And if that's what you meant when you said biased, then now the data actually do speak in your favor. The Bayes factor is now 1.12. So that's in favor of the biased. But 1.12 is very weak evidence. It would not move the needle very much. Whatever prior you started with for B has not moved. It's gone up a little bit, but not by much. Did anybody try out anything different? Did you get big values of the Bayes factor by having a different definition of what biased means? Yes?
So I restricted it to between 51 and 60, so I said moderately biased, and I got a Bayes factor of like 1.5.
Ah, okay. So if you started by saying, I think this coin is a little bit biased toward heads, so something between 50 and 60, then you ended up with a Bayes factor of about 4, which is now starting to be moderate strength evidence in favor. Okay. So to summarize, this is an example, again, where we have to wrestle with a certain amount of subjectivity. Depending on what you mean when you say biased, you might consider this data to be evidence in favor or against. Either way, it's going to turn out to be fairly weak evidence. Even if you do the bogus hypothesis, where you say, oh, it's 0.56. You look at the data, you cheat, and it still comes out with a Bayes factor of about 6, which is strong evidence, but not very strong. So that is that. Let me just see if there was anything else about Euro. I don't know what's going on out there, but it doesn't sound good. Questions about the Euro problem? All right. I think this is a good time to take a quick break. It's 11 o'clock. We're going to finish up at 12. Let's take 5 minutes, so 11:06 on my clock. Okay, let's get going again. Ahem. My word problem for geeks, if you took the SATs sometime in the distant past, you might even remember what you got. Maybe you do, maybe you don't. But imagine this hypothetical conversation. So someone's bragging and says, well, I got a 760 on the math SAT. If you're not familiar, it's on a scale that goes up to 800. So 760 is very good. Someone comes back and says, oh yeah, well, I got a 780. So I guess that means I'm smarter than you. And the question is that really true? And there are two parts of this. So one part is let's just be careful about what we mean when we say smarter. I don't want to get into a debate about that. Let's just say for our purposes, every person has some probability of getting a randomly chosen SAT question right. So if I just reach into the bin, choose a random question, you each have, maybe you have a 90% chance of getting it right, and you came in late, you didn't have things set up ahead of time, so I'm going to say you have like a 40% chance of getting it right. Well, all right, okay, so now I upgrade my belief and I'm giving you like a 60. All right, now, ignoring what smarter than means, it just means that your chance of answering a random SAT question is higher than somebody else's. And what we want to do is measure the probability that Alice's X is greater than Bob's X, given the data that they just reported. And I want to do this. This problem has it's a nice example of the kind of analysis we're doing. It's got some real world modeling decisions that we have to make, and that's one message that I want to get across. And then the other is, after you've done a Bayesian update, you very often want to do work with the posterior distributions, and this is going to be an example of that. So the approach, very similar with the coin, is that there is some unknown quantity x, and I'm going to estimate it, and then I'm going to compare the posterior distributions. One part of this that's a little tricky is that the SAT scores that you get are standardized. The score that you get between 400, is it 200? Between 200 and 800 is a standardized score based on your raw score. The raw score is how many questions you got right minus 1/4 of how many questions that you got wrong. So the raw scores, I'm going to put them on a scale from 0 to 1, which is just the fraction that you got right. For now, I'm going to ignore that penalty for getting things wrong. So this is the fraction that you got right. This is an example where I know the prior distribution because I went to the ETS webpage and they report it. So this is the distribution of raw scores across the entire population of test takers. So if I know that you took the test, but I don't know your score yet, this is what I should believe about you prior to the report. So this is a nice example where the prior is objective. I don't have to worry about that part. The likelihood function should look familiar. This is very similar to the coin problem that we just did. The only difference is the data that I get are going to be the standardized scores between 200 and 800. I need to be able to do a lookup in order to get from that to the raw score. And I've done that, again, using data from the nice people at the ETS. The people who run SAT Standard, they do a lot of really nice statistical stuff. They know what they're doing. And they publish a lot of data about it. So it's kind of a nice thing to work with. So I can figure out from your 760, I can figure out how many you got right and how many you got wrong, and I can figure out the likelihood of that outcome under any hypothetical value of x. So that's my likelihood function. Questions about that before I go on? All right, so there's some details there for the SAT, but it's basically the same as the coin problem. Here is what the posterior distributions look like for Alice and Bob. Alice, remember, got the 780. Hers is the blue distribution that's a little bit farther to the right. Bob got the 760. His is a little bit farther to the left, but notice that they overlap quite a lot. So it's quite possible that if I choose a random value from the blue distribution and a random value from the green, it could well turn out that I get a higher value from green than from blue. I'm going to get a little bit more often, Alice will win, but Bob is not going to lose all the time. What we want to do now is quantify that. So I've given you sat.py. You can run that. You'll see the distribution that I just produced. And what you're going to do is fill in PMF prob greater. I'm going to explain that in a minute. Let's take a look at the code first. So you see there's quite a lot here. I have to read the scale, and I build a data structure that allows me to do the reverse mapping, and read ranks is how I get my prior distribution, and divide values is just normalizing. The exam class contains all the information that I have about the exam, including lookup and reverse lookup. And now finally we get to the Bayesian part of this. So this is the SAT class. It inherits from suite. We've seen this several times now. And provides an init method and a likelihood method. Here is the likelihood method that we were just looking at a minute ago. Same thing. I'm going to skip this one for a minute. Ooh. And just double check something. Yes, we're good. Okay. So here's the setup. I'm going to instantiate two instances of this SAT object, one for Bob and one for Alice. I'm going to do two separate updates. So I'm going to end up with two posterior distributions, one for each of them. And then I'm going to compute the probability that Alice is smarter than Bob and the probability that Bob is smarter than Alice by looping through the posterior distributions and figuring out what's the chance, if I draw random values from both of them, that Alice's random value turns out to be greater than Bob's, or vice versa. That's what this does. Let's take a look at how it works. So this is the function that you're going to write. You're going to get two PMF objects that represent your posterior beliefs about two people, and you're being asked, what's the chance that something drawn from here is greater than something drawn from there? You have two choices for how you do this. One is you could just do it by random simulation. So you could run 1,000 times. 1,000 is a good number. Draw a random value from each PMF. And remember that there's a capital R random method that draws random values from PMFs with the correct probabilities. And just count how many times out of 1,000 does a random value from this exceed a random value from this. So that's one option. Conceptually, it's a little bit simpler. The alternative is if you want to loop through the PMFs, you can iterate all the pairs, check whether the value from PMF1 exceeds the value from PMF2, and add up the total probability. And I'll give you a little bit of the infrastructure for doing that. There's a items method. So the PMF provides items, which allows you to loop through all the x's, those are the possible values of x, and the corresponding p's, which are the probabilities. And so this nested loop is going to loop through all possible pairs. So again, if you think of a distribution as being like a bucket from which you can draw random values, what you're doing is pulling out two values, one from each, comparing them to each other, and looking at what was the probability of that pair, and adding up all the pairs that satisfy the criterion. I'll let you work on that again. You've got two versions of it. I'll come around if you have questions about that, and we'll go over a solution in a few minutes. As always, feel free to ignore me, but I filled in part of a solution here. Each time I pick an x1 and an x2, I can check if x1 exceeds x2, and then I want to increment the total by what was the probability of getting that particular pair. So that's the last thing that you need to figure out. So if you want to be very careful about this, the probability of two outcomes, that's that conjoint probability we talked about at the beginning. It's P1 times the conditional probability of x, or I should say, x2 given x1. In this case, because we're looping through the pairs, the random thing that I choose from Bob's distribution is independent of the random thing that I choose from Alice's. So this is the case where you can invoke the simple rule that says that this is just P1 times P2. I belabored that a little bit just to remind you not to apply this blindly. The probability that two things occurs is not always the product of their probabilities. That's only true if they're independent of each other.
But it does make sense to consider them independent
But in this example, it makes sense to consider them independent. And now we can run the code. Okay, so these are those posterior distributions. Again, I scaled them a little bit so that they're more visible. The scale only goes down to 70%. You can see that the distributions overlap quite a bit. And that what that's saying, that overlap means I'm not really sure who is better at answering SAT questions. And then if we do the math, the outcome is, I think there's a 60% chance that Alice is actually smarter, roughly 30% chance that Bob is, and then I've got about 10% left over, which is the probability that they're equal. And that equalness is a consequence of the fact that I've broken this range up into a finite number of values. There are two ways that you could interpret this. If you want, you could define an equivalence class that says that if they're close enough to each other, then I'm just going to consider them equal. And so you could have three outcomes. You could say, Alice smarter, Bob smarter, or don't know. Or if you want, you could also take the equal and just split it 50-50 between them, or maybe split it proportionally between them. The fine points of this are not going to matter very much. So if you like, you could say it's about 65-35. Yes? What is the purpose of the summation? So I'm enumerating all possible pairs, and I'm adding up the total probability of all the pairs where Alice is smarter. Does that make sense? Did that help? Okay. Let me suggest, if this summation doesn't make sense, then the random version might just make more intuitive sense. It says, I'm uncertain about Alice, I'm uncertain about Bob, so if I draw random values from their posterior distributions, then I'm considering possible universes that I might be in, and I'm counting what fraction of possible universes is Alice smarter in. And this computation is doing that same idea, but doing it just a little bit more efficiently. Yes, sir? Right. Yes, I'll try to repeat some of what you just said, which is that for the low values, Bob is more likely to have a low value than Alice is. For the high ones, Alice is more likely. There's a little bit of zigzag and jaggy here that just has to do with the numerics. We could smooth that out. But I think you're right that looking at this, we can't conclude that Alice is necessarily smarter. It's possible that Alice had a little bit of good luck on the exam and Bob had a little bit of bad luck on the exam. One other way to think about this is instead of trying to estimate these parameters, these unknown parameters that are inside your head, we could also make a prediction based on this. In other words, take these posteriors and we could ask, if Alice and Bob take the SAT again, what's the probability that Alice's score would exceed Bob's? Now, if we think it's 65-35, our prediction for the outcome of any particular exam is going to be a little bit less skewed than that. It might be more like 60-40 for a predictive distribution. I don't know if that idea helped or just confused the issue. Okay, so this all works out. It's about 60% in Alice's favor. That might be a little bit surprising because it's a 20-point difference in their scores, but they're both mashed up against the high end of the range, which means that we don't have a lot of discriminatory power between them. Yes? Ah, good question. If I look at the confidence intervals, they're going to overlap quite a lot. From a frequentist point of view, I might declare that this is not a statistically significant difference, right? In Bayesian land, we don't usually discretize it and say significant or not. You just report a Bayes factor that says there's a certain amount of evidence in Alice's favor. Right. Yes. Right. So the question is, I've been saying qualitatively that a Bayes factor of 4 is medium strong and Bayes factor of 1.1 is weak. People have suggested adjectives. So there are scales where for a given Bayes factor, you look it up in a table and you get the appropriate adjective. Another way to think about it is that if you started out thinking that something was 50-50, then your odds for that is 1-to-1. 50% probability is 1-to-1. The Bayes factor multiplies your odds. So if you start out 50-50 and you see a Bayes factor of 4, your posterior odds are 4-to-1, which corresponds to 80%. 4-to-1 as a probability is 80%. So a Bayes factor of 4 is evidence that is strong enough to move you from 50% to 80%. Okay. A Bayes factor of 10 would move you from 50% to 91%. And a Bayes factor of 100 would move you from 50% to 99%. Good? Let's see. Okay. I chose this example for a couple of reasons. So one of them is, again, this idea that you do a Bayesian analysis, you get a posterior distribution. That then becomes the input to a lot of decision-making processes. So in this example, we compared two distributions to see which one was larger. I mentioned cost-benefit analysis. The posterior distributions are versatile in the sense that they answer lots of relevant questions for real-world problems. The other reason I chose this example is I wanted to talk a little bit about modeling, which is all of the analysis that you do in both classical and Bayesian statistics is based on modeling assumptions. You should always remember that your results are only as good as the modeling assumptions, and that very often the errors that you quantify are very small compared to the errors that are in the modeling domain. So part of the reason I wanted to mention this, implicit in what I said is that your chance of answering an SAT question is the same for any SAT question, and by design that's not true. It's actually a good idea. If you write an exam, you want there to be some easy questions and some hard questions, because that gives you the most discriminatory power at both ends of the range. If all the questions are equally difficult, you'll be able to tell the difference between people in the middle, but the extremes will be very fuzzy. So there's another version of this that's based on item response theory that says that you have some level of efficacy, which is how good you are at answering questions, and each question has some level of difficulty, which is obvious, the level of difficulty. Your probability of answering any given question is a function of those two variables. And there are a couple of different forms that that function can take. That's what item response theory is. The model that we just did extends in a very natural way to handle it. This is in the book. If you're interested in details, take a look. But it's a nice example where something that would be really hard to do analytically is very easy to do computationally. Somebody comes in with a complicated likelihood function, no problem, you just plug it in. Everything else in this computational framework works the same way. This is the point I made a second ago, that the better as your data get better and better, the kinds of errors that you see are going to get smaller and smaller, and so it's often the case that modeling error then becomes the dominant error. So I will leave that point alone for now. But there's one related point of this, which is that some of the approximations that we've been making today, like taking something that's really a discrete value and just chopping it up into, really a continuous value, chopping it up into a bunch of discrete ranges. These are all numerical approximations. I've been very sloppy with details and things. I've done that for a reason, which is that round-off error and numerical error for these kinds of problems, those are the least of your worries. Be profligate with round-off errors, but pay attention to modeling errors. And a consequence of that is that you need to iterate. So the example that I gave in the book, I did the simple version, then I did the complicated version, and what I found is that actually, for the purposes of this problem, the answer is not very different, which is in some sense good news. That means that from now on I can forget about the complicated version, just stick with the simple version, it's good enough, which is a nice result. Okay, we are not going to take that break. I'm going to do one more case study. So you are off the hook for the last 30 minutes. I'm going to present a case study that I think you might find interesting just as an extension to what we've done so far, and then we will wrap up. So this actually came from last year's PyCon. Somebody asked me this question at the end of the session, and I thought about it, and I wasn't able to answer it live. But then, do you know the genius of the escalator? Or the genius of the staircase. I think it's, since we're in Montreal, I think it's actually a French expression. It's something like la génie d'escalier. And it's the, as you walk away from an argument, suddenly you think of all the brilliant things that you should have said. And you go back and and another thing. Similarly, I solved this problem in the shower the following morning. I found the guy and tracked him down. But here's what he asked me. I had dressed. So what he asked me is that they run a volunteer site where participants will come and they will sign up for a volunteer activity. They'll say, I'm going to go to the soup kitchen on Saturday and I'm going to work there. And then some fraction of them will then come back after the activity, check in, and say, yes, I did what I was going to do. But there are two possible outcomes. If somebody does not come back and check in, it might mean that they didn't do the activity and didn't check in, or it might mean that they did the activity and didn't check in. And what they wanted to know is, based on the statistics that we get from running the site, can we estimate what fraction of our participants are really doing what they said they were going to do? So what I did was broke it up into two pieces. That the fraction who report back, I'm going to call that P. P is the number, the percentage that actually report back. That's going to be the product of two probabilities. So Q is, did you participate? And R is, did you respond? Did you report back? Okay. Now, if all you know is how many people signed up and how many people reported back, you can't actually estimate Q and R separately. But if you can go and sample a small number of people, so of the people who didn't respond, if you can send them an email and say, did you participate or not, then you can estimate what the drop-off rate is between participating and responding. And based on that estimate, now you can estimate Q and R separately. And Q is the thing you actually want to know. So you observe P, and we're going to use that to infer Q and R, where R is the thing we actually want to know. So we're actually going to do two likelihood functions for this. Sorry, before I get to the likelihood functions, this is what the prior is going to look like. I've got a set of values from 0 to 100. I'm going to loop through all the possible Q's and all the possible R's, and each hypothesis is going to be a pair. So my hypothesis space looks like a grid, all the possible Q's versus all the possible R's. You can think of this as a two-dimensional problem. Everything about this that we've seen extends to 2 dimensions or as many dimensions as you want. You can just think of the hypothesis as being a vector. In this case, it's a 2-vector or a tuple. Okay. Now, I'm going to do two kinds of updates. So let's say that 140 people registered, and 50 of them report back and say, I did what I said I was going to do. And then I go and I survey 5 people, and I find out that 3 of them participated and 1 of them reported back. So 5 people signed up, 3 of them actually did the thing, and of those 3, 1 of them reported back. So I'm just making up this data as an example, but let's say that that's what you found out. If you do that, you now have 2 likelihood functions because you have 2 kinds of data that you observe. The first observation is the 2 values that I talked about. Sorry, I forget what my numbers were. The 140-50 and the 531. So this is the 140-50 and this is the 531. I've got 2 likelihood functions, likelihood 1, likelihood 2. This is, if you only tell me how many people signed up and how many reported back, then I'm going to loop through all the QR pairs, and for each one, compute that thing, which again should look familiar. So this is going to loop through Q and R for each pair. I get P, and that's my update. After doing that update, let's see if I have both of these. No? Okay, I thought I might have shown them both. After you do this update, you can't actually distinguish between Q and R. Your posterior beliefs about Q and R are the same. Okay? After you do the second update, now you can distinguish between Q and R. So this one's a little bit more complicated, but what I get from the data are how many people signed up, how many participated, and how many reported back. And I'm going to do 2 updates. This one is of the people who signed up, how many participated, and this is of the people who participated, how many reported. The 2 likelihoods are, again, similar structure. This is the binomial distribution that I mentioned, and the overall likelihood is just the product of the 2. This is a bit of a high-level view. If the details are not clear, that's all right. I just wanted to give you a sense of how this example works. The last piece of this that I do want to point out is what's called a marginal distribution. And this is saying if I have that grid that I mentioned for all the possible Q's and all the possible R's, I can loop through those values and I can pull out the distribution for Q and the distribution for R separately. And here's what that structure looks like. I'm going to loop through the items. Each item is going to be a QR pair. And I'm going to pull out whichever one you tell me to pull out and assemble a new PMF that has 1 variable at a time. Okay. So I start with a PMF that's full of pairs, and what I pull out is the distribution of Q and the distribution of R. And that is what they look like. So Q, again, is the fraction of all the people who signed up, how many of them participated. And it looks like I have kind of a high probability. The peak is maybe 0.65 or something in that neighborhood. But at least with the data that I chose, and again, it was hypothetical data, the fraction of people who participate and then report back is relatively low. So this says that you're probably losing about 50% of your participants who do the activity, which is great, and they just don't bother to tell you that they did it. Okay. So I wanted to show this example again because it's a two-dimensional example. Everything that we talked about today generalizes for 2 dimensions. It's also kind of a funny example because I've got 2 different kinds of data and I can do 2 different kinds of updates based on which kind of data. Summing up, everything we've looked at falls into this structure. You can think of Bayesian estimation or Bayesian statistics as a divide and conquer strategy. You figure out the likelihood function. You can put on your Bayesian blinders. You say, if I knew hypothetically what's going on in the world, can I compute the likelihood of my data? If you can solve that problem, Thomas Bayes comes and does the rest. So just to wrap up again, this is in the book, so if there are things that weren't clear, take a look there. The particular example that I just did is actually not in the book, but it is in my blog. So these are some of the case studies that are in the book. The blog, I think I have a pointer. I might not. Probably overthinking it. If you want to Google that, I can add a pointer to that. But if you find my blog, you can find the volunteer problem that I was just working on. Things that you might want to read about. I mentioned Mackay's book. His chapter 3 is a short introduction to Bayesian statistics. That's where I learned Bayesian statistics. I still think it's a really nice introduction. I stole several of my examples from him, so take a look. And that book is now available as a free PDF. The other free book that I recommend is Cameron Davidson Pilon's book. He is probably here at PyCon, so you might get a chance to catch up with him. Bayesian Methods for Hackers, also a free book. That's all on GitHub, and it has a lot of IPython notebooks that let you execute the code as you go along. So I'd recommend that book. And here are a couple of books. These are all in the slides. These are not free books, but they're kind of a good library of Bayesian methods. These are more mathematical. So my thesis here is that you can get started with a lot of Bayesian stuff without doing any math. This is the approach that I like is, well, this is the usual. People start by doing a lot of analytical distributions. They do a lot of mathematics, which means Bayesian statistics, if you just pick a random Bayesian book and open it to a random page, there will be nasty integrals all over that page. And then in order to solve those integrals, you normally have to break out numerical methods. What I'm suggesting is kind of the other way around, which is if I'm going to do a bunch of analysis in order to get an integral that I can't solve, and then break out numerical methods to solve it, why don't I just start with numerical methods in the first place? So that's what the approach that I've presented is. I think one benefit of this is that using these computational tools, you can think more about the nature of your problem. What's the right prior? What's the right likelihood function? What are the modeling decisions that I have to make? You can experiment quickly. You can do rapid prototyping. And then once you've got something that you understand, you've got it debugged, you believe it's doing what you're doing, now if you have performance problems, there are a lot of things that you can do to speed it up. So this is what I mean when I say start with brute force solutions. Everything that you've seen today, all of these for loops, you're basically you are looping through all the possible outcomes. As the number of dimensions gets big, this becomes infeasible fairly quickly. But there are a couple of places where you can jump off and try something else. If it runs fast enough, you're done. If it doesn't, you need to do some optimization. 2 options for that optimization. One of them is MCMC, Monte Carlo Markov chain, possibly the other way around. Got it right? Which is implemented in PyMC, which is what Cameron Davidson Pilon's book is about. So I think it's a nice progression from this workshop and or the Think Bayes book into that stuff, which is one way of optimizing. The other way of optimizing is to break out the analytic methods. The analytic methods can take some of the things that I've done where you're looping through possible outcomes, so it's linear in the number of hypotheses. The analytic methods can often make that constant time. And there are some examples of that in the book. If you are working on interesting Bayesian problems and like the person who asked me about the volunteer question, you would like some help with it, I can possibly help you with that. As of June, I will be on sabbatical for a year, so I'm looking forward to that and always looking for interesting things to work on. That is all I'm going to do for now. I can take some questions, and you should fill out the survey. If things have gone according to plan, this link should take you to the page for this tutorial, and in the lower right-hand corner, let's see if this is going to work for us. Possibly slow because you're all doing the same thing at the same time. There we go. So this is the page for this tutorial, and here under feedback, you will find tutorial survey. Click on that. And you can fill that all in while I'm answering questions. Important point, there are 2 L's in excellent, in case you want. Yes, sir.
One of the really cool things about Bayes is the ability to incorporate arbitrary data into your Poisson distribution.
Mm-hmm.
You start with a 50-50 prior, and then you say, given the likelihood that the sun has still risen, how does that change my results?
Mm-hmm.
So that's what I've read. I've always been very confused about how that actually works. How do you take data that aren't necessarily on the same scale, they pertain to different things, and combine them into a Bayesian inference?
Good question. I'm going to try to repeat it because people won't have heard it. So one of the nice things about this is that you can work with very different kinds of data. So you start with a prior, and any kind of data for which you can define a likelihood function, you can do an update. So the volunteer example was one where I've got 2 different kinds of updates that I do with different kinds of data. You also mentioned an example that comes up when people think about, what is the probability that the sun will come up tomorrow? How should I think about that from a Bayesian point of view? In some sense, the fact that the sun has come up every day of my life so far should increase my belief in the probability that it will come up tomorrow. But in order to do that in a Bayesian framework, I need a model of the likelihood of the data under each hypothesis. So one hypothesis is that the sun will not come up tomorrow. The other is that it will. And so what I need to say is, what is the likelihood of seeing 47 consecutive years of sun if the sun comes up every day? And what would the likelihood be in some alternate universe where it comes up for 47 years and then doesn't? So the sticking point there is similar to what we ran into with the Euro question, which is that the first hypothesis is kind of easy to model. The second hypothesis, I need to be more specific about what kind of universe would that be where the sun comes up for 47 years and then doesn't. But if you can specify that model, then you can fit it into a Bayesian framework. That's the sticking, for that particular example, that's the sticking point. Yes?
How do you deal with distributions that maybe unbounded, or if not unbounded, just over many orders of magnitude, so that discretizing is either not practical?
Great question. So how do you deal with distributions that are either unbounded or they span many orders of magnitude? So discretizing them in linear space doesn't make sense. There are a couple of options. So one of them is to discretize them in log space, and that works well for a lot of these things. Another possibility is, even though you know that it extends forever in theory, you can truncate it for practical purposes, and then you can check to see whether your truncation is messing up the results. So you could run this a couple of times with different priors where you gradually move that bound, and at the point where it stops mattering anymore, you could say, yes, it's infinite, but if I truncate it, it's close enough. I think there's an example of that in the book. Actually, I did that with the train problem. The train problem is an example that is very sensitive to the upper bound that you choose, especially when you have a small amount of data. As you get bigger and bigger, you get less sensitive to the choice of the prior. Good. Other things, yes?
For that example, couldn't you also think of them as Gaussian distributions or something? Because those are unbounded, right? They just kind of stretch on into infinity and are just super unlikely the farther you go out.
Yes. So one possibility is I could choose distributions that actually do extend forever, like Gaussians. But for the brute force method that I used, where I have to discretize everything, I'm still going to have to cut it off somewhere. But for the analytic methods, that works very well. And so, yeah, Gaussians and exponentials, things like that, behave well for these methods. Anything else? Great. If you think of things, I have one more slide that has all of my contact information. Just pull that up. Questions? Oh, maybe I didn't put it in. Well, you do have my contact information. So send me email if you think of things or hang around and ask questions, but we are done. Thank you all very much. It's been great.